in this semester. So limiting reactant, I think both of you already took that quiz, if I'm not mistaken. Grades for the quiz actually looked pretty good for most people. But, okay, so I think I just saw Aiden's then maybe. I just graded a bunch of them, so who knows. Oh, this says January 5th. That is wrong. That is from last year, for sure. So we will adjust that real quick. So limiting reactant problems and percent yield, how are they related? Well, they're pretty much the same, right? Percent yield, we're just going to do one additional step beyond a limiting reactant problem. So again, we're going to just identify the steps and use the steps to solve a limiting reactant problem. And I probably should add to that, including percent yield. So we talked a little bit about, you actually love percent yield? Yes, it's easy, right? It's easy. It's just a formula. Again, though, getting to the actual theoretical yield can be difficult. So these were the steps that we looked at last week. Bella, I loved that you used these on the quiz. That really made me happy because it showed me that, one, you were following the steps, and two, that this helped you to have the steps sort of outlined, right? It helps me for sure, because otherwise you can get lost in these problems. So just to review our steps from last week, balance the equation is the first one. Identify what they tell you in the problem is the second one. Determine if this is actually a limiting reactant problem, which we talked about for all of ours, right? It seems obvious, but in the future, you may see questions where it could be limiting reactant, but could be something else. Do your stoichiometry calculations for both of the reactants and figure out which one will produce the least amount of product. And then the lower answer is the theoretical yield of the product, which then tells us that is our limiting reactant. Now, today we're going to continue with that concept and actually practice one limiting reactant question, and then we'll go into percent yield. So, how many grams of, I believe that's zirconium chloride, can be produced if 123 grams of zirconium silicon oxide react with 85 grams of chlorine gas? I'm guessing it would be a gas. So, no, it's fine. I'm going to give you guys, I don't know, what do you think? Like 5 minutes to go through this question and try to solve it as a limiting reactant problem. So remember our steps here. Balance. What's given. Limiting reactant. Stoichiometry. And then figure it out or identify limiting reactant. All right, so I'm going to give you guys 5-ish minutes. I'm also going to be solving this, and then we'll go over it. So let's start our 5 minutes right now. All right, how you guys doing over there? I just finished the question. So, which one is the limiting reactant? Is it the zirconium silicon oxide or the chlorine? Bella says not quite done. Okay, I'll wait. But when you are done, just pop into the chat which one of the reactants you think is the limiting reactant, and then we will discuss. Hi, Vitali. We're working on solving this limiting reactant problem, but we're about to discuss it. So if you want to maybe start it or review the process while we wait here. But we're waiting for everybody, including Aiden and Oliver, to mention which one of these reactants they think is the limiting reactant. And there's only two choices, so if you're not sure, you can always guess. All right, so Bella, even if you're still working here, I haven't seen anyone tell me which one's a limiting reactant yet. So we're going to go through at least how to do this for the zirconium silicon oxide. And then the chlorine one's actually a lot faster. This one just takes the longest time because it has a huge formula here. So the first step is balance our equation. Well, conveniently, the equation's already balanced, right? I actually balanced it for you, probably accidentally. So the 2 is already in front of chlorine, which would have been the only thing we needed to do. Otherwise, it's balanced. So then we look at what's given. Well, we're given the grams of one reactant and the grams of the other reactant. So we're basically told how much zirconium silicon oxide we have and how much chlorine gas we have. What we want to know is how many grams of zirconium chlorine or chloride can be produced. So our first step then we check, is this a limiting reactant problem? Well, yes, because we know information about both of the reactants. We're trying to figure out which one's the limiting one. So then we do some dimensional analysis, right? We start with our amount of our reactant, zirconium silicon oxide, 123 grams. Well, we need this in moles, right? Because remember, we can't do our coefficient ratios if it's not in moles. So in order to get to moles, we need our molecular mass, right? Or our molar mass of zirconium silicon oxide. So if we look on the periodic table and we add all those things up, zirconium's like 91 point something. Silicon is, is 28 point something, and then oxygen is 15.999. So if you add up 4 oxygens, 1 silicon, and 1 zirconium, you get 183.306 grams. That's per 1 mole, right? Then we look at our equation, we look at our coefficients. We see that for every mole of zirconium silicon oxide, only 1 mole of zirconium chloride is produced. So therefore, they have a 1-to-1 ratio, just 1 mole over 1 mole. And then we convert the other way back to grams of moles of zirconium chloride. Oh, whoops, I accidentally wrote an I there instead of an R. Which again, to find the molecular mass of that, you just add zirconium, which is like 91, plus 4 chlorines, which are 35.453. So you should get 233.02 grams per mole for the zirconium chloride. So if you do all that and you multiply it all out, you end up getting that 156 grams of zirconium chloride would be produced from this amount of zirconium silicon oxide. Then we have to do the chlorine the same way. Literally the same steps, just with chlorine. It's much faster. Chlorine only has 2 chlorines, right? Much easier to find the molar mass there. And Bella, you are 100% correct. The limiting reactant is chlorine, because the chlorine will only produce 139.68 grams of zirconium chloride, which is about 20 grams less than the zirconium silicon oxide would produce. So in this case, chlorine is our limiting reactant. Now, that would tell us then exactly what Bella wrote in the chat here, that 139.68 grams would be our theoretical yield, right? We talked about this last week. It's a theoretical number because it's what we should get. Most of the time, you're not going to get your theoretical yield. Why? I mean, it could be for any reason of things. The temperature wasn't right. You added a little bit more than you thought you added, right? Because we're talking very exact numbers here. You let the reaction, sit around for too long and some of it reverted back, right? There's a million ways that you could mess this up, essentially. So theoretical yield is great, but then what we're going to talk about today is percent yield. Well, we want to know, how close were you, right? So part of chemistry is, here's what the theory says. Can I replicate that in a lab? Again, the answer is, can you make it perfectly? Probably not. However, your percent yield is going to tell you quite a lot. For example, if you have a really high percent yield, right? What does that mean? Well, let's figure it out. So let's say we're going to use our number that we just got for our zirconium chloride. Let's say that our theoretical yield is 139.68 grams of zirconium chloride, right? And let's say that we actually get 121.42 grams of zirconium chloride, right? We did the reaction, that's how much we got. Pretty close, right? That's not terrible. But now we would want to know, well, what would be our percent yield? Let's say that that's what Bella got. Let's say that Aiden got much less, 75.24 grams. Because we're going to look at both of these and we're going to look at the pattern here. So percent yield's pretty easy. You do the actual value you got divided by what the theoretical yield is times 100. So if we were going to examine Bella's to find out the percent yield, right, which she just did, we would get 86%. Okay, well, let's just write that out just in case people are having a hard time visualizing. We would do 121.42 divided by 139.68, and then we would multiply that whole thing times 100, and we would get 86%. So what about our other one? If the if our actual yield was even lower, 75. If our actual yield is 75.24 and our theoretical yield is 139.68, and then we multiply that by 100, what would our theoretical yield be for our second situation here? Oops, I didn't mean to put so many slashes in there. You guys can use a calculator for this, by the way. 75.24 divided by 139.68 times 100. Easiest math we've done in the class. Thank you, Oliver. 53.8%. Okay, so what would we say then is the pattern? What is the percent? Oh, oops, I did this backwards. What is the pattern here? Does percent yield mean if you have a high number of percent yield, is that a good thing or a bad thing? So if 86% is our percent yield, is that good? Does that mean we were close? Or does that mean that we were really far away? Any ideas here on the relationship? Can I repeat it? I certainly can. If we have a high percent yield, 80%, 90%, 100%, is that good? Does that mean we did well? Yes, right? So the closer to 100% you are, just like in school, the better you did, right? So if you got 100%, that would mean that you did the reaction perfectly. You had absolutely no error. Again, that's probably not achievable. Usually, if you're getting above 85%, that's pretty good. And there are some reactions where you can't get to that, right? Because of different situations and special things happening in that specific reaction. So keep that in mind, right? This is going to depend on the reaction. Some reactions are easier to do than others, just like school. Some assignments are easier to do than others. Okay, so now we're going to put all of this into practice, where we're going to do a full problem. And we'll probably just do one here, and I'll give you another one to do as a bonus, if you'd like. Okay, so here's our question. 9.8 grams of magnesium metal react with excess hydrochloric acid, and 29.8 grams of magnesium chloride are produced by the reaction. What is the percent yield of this reaction? Now, this is very similar to a limiting reactant question, but it is not the same, because notice we're not being asked for the limiting reactant. In fact, we're told which one of our reactants here is our limiting reactant. They tell us in the problem. Which one's our limiting reactant, magnesium or hydrochloric acid? Magnesium. Okay, thank you, Vitali. Yeah, magnesium is our limiting reactant. Why? Because they tell us this very important word, excess hydrochloric acid. That means you can use as much as you want. That means we're limited by how much our magnesium, our 9.8 grams of magnesium can produce. Right? We can add as much hydrochloric acid as we want. So that's great. We don't have to do all the work to figure out the limiting reactant. However, we do need to know the theoretical yield, which we do the same way as we would in a limiting reactant question. So again, first step is always going to be balance our equation. Our equation's not balanced here, so we will check. Let's see. Magnesium here, 2 chlorides on this side, 2 hydrogens on this side, 1 of each here. So we're going to have to place a 2 in front of our hydrochloric acid. Now we know magnesium is our limiting reactant. Our limiting reactant will give us our theoretical yield, right? Because we will use all of the limiting reactant, and then that's as much as we can possibly produce. So we set this up the same way that we would a limiting reactant question, where we say that we have 9.8 grams of magnesium. Well, we need to convert to moles. Why? Because we need moles to look at our coefficients in our equation. So we find magnesium on the periodic table, and we see that there are 24.305. 24.305 grams of magnesium in 1 mole of magnesium. Okay, then we're in moles. Now we need to use our actual equation here, right? We are producing specifically here magnesium chloride, because that's what they told us that we really got. We really got 29.8 grams of magnesium chloride. Well, how much theoretically should we have gotten? So we're looking at magnesium chloride here as our product. So we want to find our ratio. Well, we just have 1 mole of magnesium to 1 mole of magnesium chloride. So we don't need to do anything here except write it in. Oh no. This is the problem with trying to do this in annotations. It's never as nice. Okay, 1 mole of MgCl2. And underneath that, we have 1 mole of Mg. Right? For every mole of magnesium, we just get 1 mole of magnesium chloride. And then again, now we need to go and convert back to grams. Because again, we want to know how many grams would theoretically be produced. So we need to figure out how many grams are in 1 molecule of magnesium chloride. Magnesium is 24.305. Chlorine is 35.453. So we get 95.211 grams of magnesium chloride in 1 mole. So we check to make sure our dimensional analysis is going to work out, which it looks like it's going to, but never hurts to check. We got grams canceling with grams. We got moles canceling with moles. We got moles canceling with moles. And we are left in grams of magnesium chloride, which is exactly what we want. So now we do our math. 9.8 times 95.211 divided by 24.305. And we get 38.389 grams. Now, that's our theoretical yield. What were we even being asked in this question? Oh yeah, our percent yield. So how do we find our percent yield? In case we forgot, we flip back to the previous slide, if it will let me, which it does not want to let me. We have our actual over our theoretical times 100. Okay, so I'm going to plug all those things in. We have 29.8 grams was our actual value, divided by our theoretical value of 38.389. We times that by 100, and we get something once I calculate it, but you should be calculating it with me at the same time. Okay, divided by 38.389. We get 77.6%. So that is our percent yield. We produced 77.6% of what we should have produced. Not terrible, but not that great, right? So again, very similar to how you would do a limiting reactant problem in terms of the stoichiometry, right? That is staying the same, where you're converting between grams, moles, using the coefficients from the balanced equation to convert between moles. And then you just have to add the extra step of doing the percent yield equation, which isn't so bad. So let's try one more, because that actually didn't take as long as it could have. Percent yield's usually pretty fast. Okay, so when Mandy allows 38.5 grams of oxygen to react with 4.05 grams of hydrogen gas, she is able to collect 35.3 grams of water. What is the theoretical yield of this reaction? And what is the percent yield? So now we're being asked for two things. Theoretical yield, which is going to come from our stoichiometry, and percent yield, which is going to come from our equation. Okay, so you guys let me know in the chat. Do you want me to walk you through how to do this one? Or would you like to try by yourself first? Put a 1 in the chat if you want me to go through it. Put a 2 in the chat if you would like to try by yourself. And Bella is pointing out something that is going to be a key point, which is you have to figure out which one is the limiting reactant. They don't tell you, right? So you won't know unless you figure out. So that would be a good first step. Which one's the limiting reactant? That will also tell you the theoretical yield, right? So you'll kill two birds with one stone. Okay, so you guys both said try by yourself here. So let's do 5 minutes. Again, right? Take all the information you know from here. Start with balancing. Make sure your equation's balanced. And I'll check back in with you guys in 5 minutes. All right, how are you guys faring over there? Did you at least figure out which one's a limiting reactant yet? Oh, Bella's ready. Okay, the theoretical yield is 36.1 grams water. Yes, you're 100% correct, right? And what was the limiting reactant then? Because that's exactly what I got. And which reactant caused that, Bella? Hydrogen. Good. So hydrogen was the limiting reactant, right? We could probably guess that because we only had 4 grams of hydrogen and 38 grams of oxygen. But hey, you never know, right? You got to always check. So you're right. Our theoretical yield was 36.1, right? I got 36.4, but very slight difference there. And our percent yield is then 97%. That is very high, right? That is an excellent percent yield. That is almost perfect. Now, again, this looks like a pretty easy reaction, right? We have 2 things coming together. It's a synthesis reaction. Under certain conditions, it would happen perfectly. Okay, so that is going to be it for the end of this session. This should help you now have skills for the percent yield quiz if you haven't done it yet. Next week, we don't have a virtual session, right? This is our last one. We also won't have a ton of assignments due for the rest of the semester, so use that time to go back and revise. I just put in a ton of zeros today, so go check your grade, right? You have so much time to make your grade your dream grade right now. So use it. If you want to redo on a quiz, let me know. If you return in an assignment, right, I'll regrade it and you could get a higher grade. Make sure you've done a collaboration project. Some people have not done one yet. But otherwise, this is the final virtual session. And I'm not going to give any bonus points here since participation was questionable by some of us in this session today. Bella, if you would like to add points, since you did communicate pretty intensely the whole time, I will give you some extra points if you need them. So just hold on to them if you'd like. Otherwise, guys, virtual sessions are for you, right? If you're not talking to me, I don't know what you understand, what you're confused on, right? If you're not getting out a calculator or typing it in your computer to do basic division, right? That tells me that you're being lazy. So make sure that you're actually attempting to participate in these things, even if you're saying, I'm not sure, I got this, or you're guessing. Especially when I ask a question like, is it oxygen or hydrogen? And you're like, complete silence. Okay, otherwise, I will see you guys next semester for Chemistry B, where we will resume our virtual sessions. Probably the second week of the semester is usually when they start for me. So I'll be sending out emails and stuff about that. Otherwise, please communicate with me if you're needing help or you need something redone for your grade or whatever you need, right? Because we got just a few weeks left here. So I will see you guys virtually in the next semester. Otherwise, I will hopefully talk to some of you through email before then. All right?